Hello, everybody. This is the third lecture on the topic metal semiconductor contact. In this lecture, I will discuss the current voltage curve of a metal semiconductor diode, also known as Schottky diode. Um, I will introduce the thermionic emission model. I will apply it to the diode where the semiconductor is of N-type. And finally, in the last slide, I will tell you what changes in this model if the semiconductor is of p-type, even though the p-type the p-type semiconductors are used in industry, in industrial applications, almost never, extremely rarely. Mostly like 99.99999% of the cases. I do not know how many nines there are under the decimal point. N-type semiconductors are used to produce industrial Schottky diodes. All right. Anyway, so let's begin with qualitative considerations. Let's say your semiconductor is of N-type. This is the energy band diagram of the diode. An ideal diode when no voltage is applied to the metal. So we assume the semiconductor is grounded, voltage V will be applied to the metal. The work function of the metal is higher than that of the semiconductor, and this results in a Schottky barrier right here, which prevents electrons to enter from the metal into the semiconductor. Also, the band bending of the semiconductor, so the semiconductor bands are bent up, which means that there is a depletion region. The characteristic trait of a metal semiconductor diode is that the semiconductor must have a depletion region at zero applied voltage. So there is a depletion region formed in the semiconductor when no voltage is applied. So you see the Fermi energy at the interface right here is actually a little bit closer. Maybe the way I drew this diagram implies that there is not only a depletion region, but also an inversion layer somewhere here at the boundary. Okay, but this is just schematics. Inversion layer will not play a role in the theory of current voltage curves. So there is definitely a depletion region right here. So there are two currents. When the metal and the semiconductor are in equilibrium with each other, then there are two currents which perfectly balance each other. These are the flows of electrons from semiconductor into the metal and from metal into the semiconductor, and at zero applied bias, zero applied voltage, the two currents mutually cancel. In order to make it into the metal, the semiconductor electrons, which live in the conduction band, need to overcome this energy barrier, which is given by the product of the elementary charge and the built-in voltage. And in the simplified and the idealized diode model, the built-in voltage is simply the difference between the metal and the semiconductor work functions. Whereas for electrons that try to make it from metal into the semiconductor, the energy barrier is a little bit higher, Schottky barrier. So the typical height of the Schottky barrier is a few tenths, so 0.5, let's say, or 0.6 or 0.8 electron volts, whereas the built-in voltage is maybe 0.2 electron volts or something like that. Now, the built-in voltage is much lower than the Schottky barrier, but which means that it is much easier for electrons to enter metal from the semiconductor side, but there are the concentration of conduction electrons in the semiconductor is much lower than the concentration of electrons in the metal. So these two effects, the lower barrier but the lower concentration of electrons, make the two currents from the semiconductor into the metal, and from the metal into the semiconductor mutually balanced. Now, when you apply a positive voltage to the metal, this means that electron energies on the metal side becomes smaller, because electron energy is affected by the value of the electric potential, as the energy gets reduced by the amount electron charge, negative elementary charge, times the applied voltage. The electric potential decreases by the applied voltage. No, the electric potential, increases by the amount of the applied voltage by V. So the electron energy gets smaller by negative EV. As a result, the Schottky barrier doesn't change, because this barrier is very large. It is very sharp on the metal side, if you see this barrier. So the Fermi energy of the metal goes down, the vacuum energy of the metal goes down by the amount EV, but also the top of the Schottky barrier goes down by the same amount EV. So the Schottky barrier doesn't change. Whereas the energy barrier needed for electrons in the semiconductor to make it into the metal gets reduced by the amount EV. So this means that more electrons will be able to enter the metal from the semiconductor side, whereas the number of electrons able to overcome the Schottky barrier and enter the semiconductor from the metal side will remain unchanged. Okay. All right, so now let's start building the quantitative theory. Those were the qualitative considerations. Now let's start building the quantitative theory. Let us write down the total flux of electrons from the semiconductor into the metal. Let us denote it as J S to M, and it depends on voltage. And the total flux of electrons from metal to the semiconductor is denoted as metal JMS, metal to semiconductor, right? So I hope this notation is self-explanatory. So the total flux of electrons, the total flux density of electrons is the sum of the two. And the metal to semiconductor flux, because the barrier, the Schottky barrier, does not change as you apply a voltage to the metal, then the metal to semiconductor flux of electrons also does not change. It is a constant. It has the same value when the voltage V is applied to the metal as when no voltage is applied to the metal. And let us call this metal to semiconductor flux, let us call it the saturation flux density of electrons. Now, okay, so it is fixed. Let us just call it J sub S, saturation flux density. Now, the semiconductor to metal flux depends on the applied voltage, because, sorry, oh, the light went off, now it's on. Because the barrier height decreases as you apply positive voltage to the metal. And this means that the number of electrons which are able to overcome the barrier height will become bigger, but by how many times it gets bigger? So we have this Boltzmann factor that gives you the number of electrons, which is proportional to the number of electrons with a particular energy, right? It is exponential to the power minus energy divided by kT. It is the probability, so strictly, more precisely, the Boltzmann factor, exponential to the power negative energy divided by kT, is the probability for a quantum state with a particular value of energy to be occupied by the electron. And this probability is evaluated within Boltzmann's approximation. Now, this Boltzmann factor increases for semiconductor electrons. It increases with the applied voltage. So the probability for an electron to have the energy higher than the barrier height increases by how much? By this Boltzmann's factor, exponential to the power EV over KT. EV is by how much you decrease the barrier height, right? Now, KT divided by the elementary charge E is the thermal voltage. We do not want to use the same letter E as the base of the natural logarithm and also as the elementary charge. Notationally, this is clumsy. So KT over E elementary charge is the thermal voltage. So we conclude that the semiconductor to metal contact must increase as exponential to the power V over the thermal voltage V thermal, where V is the applied voltage. What is the prefactor? Now we know that in equilibrium, the metal to semiconductor, so in equilibrium when no voltage is applied, when voltage is zero, the metal to semiconductor flux density and the semiconductor to metal flux density must perfectly balance. So when voltage V is zero, then the semiconductor to metal flux density, J semiconductor to metal, has the value opposite to the J metal to semiconductor flux density. No. All right. So J semiconductor to metal at zero voltage is JS. Now I probably should put a minus sign here to negative JS to indicate that the metal to semiconductor current flows in the opposite direction as the semiconductor to metal current. No, sorry, everything is correct. So at zero voltage, J semiconductor to metal is negative J metal to semiconductor. Everything is correct. And it has the value negative J sub S. Yeah. Everything is correct on this slide, including the signs. So now we can write the expected functional form for the total electron flux density, which is the sum of the metal semiconductor and semiconductor to metal contributions. The semiconductor to metal contribution is negative Js times exponential V over V thermal. Okay, and the metal to semiconductor contribution is positive Js. But now this is the flux density, or the particle flux density. How about the electric flux density, the electric current density, to use the more precise terminology? Electric current density is the product of flux density times the electron charge, which is the negative elementary charge. So the current density is the saturation current density, which is elementary charge times J sub S times this. So capital JS is elementary charge times lowercase j sub S. And this gets multiplied by this exponential to the power V over V thermal minus 1. So this is the current voltage curve, expected current voltage curve for over Schottky diode. Good. So the next question is, how do we figure out the saturation, reverse saturation current density J sub S, this one? This is our main task now. Let me begin by reminding you something from the kinetic theory of gases. Now we are going into the thermionic emission theory. Imagine you have some volume filled with a gas, and the gas is kept at temperature T, and we know the concentration of the gas molecules, how many gas molecules per unit volume. We know the mass of the gas molecules, and we ask ourselves, let's say we want to figure out the pressure on the walls of this vessel in which the gas is. We ask ourselves how many times, on average, do the gas molecules hit the surface of this vessel, of this container, per unit surface area. The frequency of these kicks is measured, so it is the number of kicks per unit time per unit surface area. So this frequency of kicks, let's call it J, is measured, lowercase j, is measured in the same units as the particle current density or the particle flux, that is inverse centimeter or meter squared inverse second. Okay. All right, so now we wish to figure out express this frequency J in terms of the known parameters. What can it depend on? It can depend on temperature. It can depend on the concentration of the gas molecules. Well, it is clear if you double the concentration of molecules, you will double the frequency of those kicks. If you increase the temperature, that means that your molecules are now moving faster on average, and so they collide with the surface more frequently again. But if the mass of the molecules increases, then the number of kicks will be not as sensitive to temperature as for lighter molecules, because the heavier a particle is at a fixed energy, the heavier the particle is, the slower it moves at a given energy value, right? Okay, so now we use the dimensional considerations to combine these three parameters: temperature, concentration of gas molecules, and the atomic and the molecular mass, into something which has the right dimension of the number of kicks per unit surface area per unit time, meters to the -2, seconds to the -1. Okay, so temperature. Temperature is measured in kelvins, and Kelvin is not really a C unit. It's not as fundamental as the energy unit. And luckily, we know how to convert temperature into thermal energy. We just multiply temperature by Boltzmann's constant K. So KT is the thermal energy, and as energy is measured in Newton meter, that's joule, and Newton is kilogram meter per second squared. So thermal energy is measured in kilogram meter squared per second squared. Gas concentration is measured in inverse cubic meters, right? And the mass is measured in kilograms. So how do we combine these parameters to get the right quantity with the right dimension? Well, this is the only combination that you can come up with. Concentration of gas molecules times the thermal velocity of the gas molecules, which is the square root of thermal energy divided by the mass. Okay, so we have derived a very powerful formula without much effort. We just used dimensional considerations. Now, of course, dimensional considerations do not tell you anything about the proportionality constant. Dimensional reasoning can allow you to draw conclusions like J is proportional to n square root of kt over m, but it doesn't tell you what the proportionality constant is. And the more precise calculation based from the kinetic theory of gases the result is that the proportionality constant is 1 over square root of 2 pi. Yeah, 1 over square root of 2 pi. All right, so that's the result, and now we wish to apply this result to our electrons which are in the semiconductor. So we need to find the semiconductor to metal current, which is the reverse saturation current density, using this formula that we have obtained from the kinetic theory of gases. What do we need to do? Well, we need to replace we need to make two replacements. we need to replace the electron mass or the molecular mass m in that formula with the electron effective mass. Now the concentration of molecules in a gas needs to be replaced with the concentration of electrons. But what electrons? Only those electrons which are able to make it over the barrier, over this barrier into the metal. Okay, so now this concentration can be found by following the same procedure we used to determine the electron concentration in a semiconductor in equilibrium. And you remember that result, and see the effective density of states times the square root of the effective density of states times exponential to the power negative EC minus E Fermi over KT. So we need to, in order to be able to make it out of semiconductor into the metal, the energy of the electrons must be higher than the energy at the bottom of the conduction band, plus this extra energy, the barrier height, which is the product of the built-in voltage times the elementary charge. So the concentration of electrons with this energy higher than this value, EC plus E times V built in, let's call it N star, is obtained by integrating the product of the Fermi-Dirac probability density, which is approximated as Boltzmann function, times the density of states in the conduction band. But the integration limits should be not EC to infinity, but this lowest energy, EC plus E times V built in to infinity. Right? Because we are interested in the total concentration of electrons with energies higher than this value. And this integral is easy to evaluate. That we have already done this when the lower integration limit was just EC, and we can just repeat the steps in this evaluation. This is the final result. The result is the effective density of states, NC, times exponential to the power minus the Schottky barrier divided by the thermal voltage. And the effective density of states is given by the formula that we have obtained earlier, where the electron mass is the density of states effective mass. So in this formula for the reverse saturation current density, the electron effective mass is the density of states effective mass, not the conductivity effective mass. All right, so okay, so we got our expression for the semiconductor to metal current, flux density, when 0 voltage is applied. NC times exponential to the power minus the Schottky barrier height over the thermal voltage is the concentration of electrons whose energy is higher than the barrier height. This part gives you the electron flux, the total electron flux from the semiconductor side onto the interface, the boundary between the metal and the semiconductor. And finally, we multiply this result with the electron charge, negative elementary charge, and combine with the previous formula with, this formula, right? With this formula. And using this formula, we obtain the current voltage curve of a metal semiconductor junction diode, Schottky diode, where so Js, capital J sub S, is the reverse saturation current density. It is given by this thing. this expression, multiply it with the elementary charge. Now, NC, the concentration, effective density of states in the conduction band is given by something which is proportional to kT times the electron effective mass to the power 3/2. Here it is, right? So combining these factors, kT and the electron effective mass, oh, by the way, this electron mass is also density of states effective mass. Yeah. So combining everything together, we find that the reverse saturation current density is so temperature turns out to be raised to the power 2 because kT is raised to the power 3/2 in the effective density of states, but then you have kT to the power 1/2 in here in the square root. So altogether, this gives you temperature to the power 2. And the electron effective mass, kT, the effective density of states contains the effective mass to the power 3/2, and it is divided by the square root of the electron effective mass. So electron mass is raised to the power 1. And I just corrected a typo in this constant. All right, so the reverse saturation current density turns out to be proportional to the temperature squared. It contains a factor exponential to the power negative Schottky barrier divided by the thermal voltage. And the proportionality constant is called the Richardson-Dashman constant. It is obtained by combining everything else in this formula. It has the value of 120 amperes per centimeter squared per Kelvin squared, multiplied with the ratio of the electron density of states effective mass to the mass of a free electron. Yeah, because we replaced this electron, we had to use the density of states effective mass here, and we can change this to free electron mass, but then we need to multiply by this ratio, effective mass over free electron mass. Now, the typical value of the Schottky barrier is of the order of half an electron volt, give or take a few tenths of an electron volt. So the reverse saturation current density, it turns out to be quite high. It is in the milliamp per centimeter squared range, maybe even higher, tens of milliamps per centimeter squared. And this is what makes the Schottky diodes different from the p-n junction diodes. In Schottky diodes, you are using the majority carriers, but in p-n junction diodes, it is the minority carriers which participate in the current formation. So because of that, the reverse saturation current density is much higher in Schottky diodes than in the p-n junction diodes. Now, what changes when you are using a p-type semiconductor for your diode? Well, for that, you need, in order for the p-type semiconductor metal junction to be used as a diode, you need the semiconductor work function to be higher than the metal work function, which means that the semiconductor must be doped much heavier than in the n-type semiconductor case, right? But this also implies that the mobility of your charge carriers, of your holes, majority carriers, will be much smaller if you are using p-type semiconductor. So this is one of the reasons, and so that the currents that you will get for forward bias will be smaller, much smaller. And this is one of the reasons why p-type semiconductors are used extremely, almost never in commercial or industrial Schottky diodes. Another reason is related to the effects that we have not included in our considerations in this theory of ideal Schottky diodes. We have not included such things as Fermi level pinning to the middle of the band gap. We haven't included the non-ideal effects such as the lowering of the Schottky barrier due to the mirror reflection forces. We did not include, oh gosh, we didn't include a lot of things. Did not include the generation of charge carriers in the space charge region of the semiconductor and at the interface. And all these effects result in a large leakage current in the semiconductor metal Schottky diode. And it turns out that this leakage current is higher, significantly higher, if the semiconductor is of p-type than if it is of n-type. But for theoretical academic interest, we would like to also understand how an ideal Schottky diode works if the semiconductor is of p-type. So what changes? Well, in that case, the current voltage curve changes polarity, because if you apply positive bias to the metal, this would make the current small. You will be in the reverse saturation regime. So in order for the junction to work, to have large current, you need to apply negative bias to the metal, so the polarity changes. Oh, by the way, this is the symbol in diagrams for Schottky diode. So the direction of this triangle shows the direction of positive bias when the large current is flowing, right? So the current prefers to flow to the right in the diagram. And if in the case when the semiconductor was of n-type, the large current was flowing from metal to the semiconductor, right? When the semiconductor is of p-type, the large current will be flowing when positive bias is applied to the semiconductor and the metal is at the negative bias. Okay, the Schottky barrier height, in this case, when the p-type semiconductor is used, is given by a formula which differs from what we had in the n-type semiconductor. Namely, you need to add the band gap to this formula. So the barrier height is now measured between the bottom of the valence band at the point of contact or in the junction plane and the Fermi energy of the metal. So this is your Schottky barrier, because it is this barrier which electrons need to overcome in order to make it from the semiconductor valence band into the metal. Okay. The size of this barrier is also easy to understand. So E chi is this energy difference. E gap is this energy difference. And E psi metal is this energy difference. So you subtract E psi metal from E chi plus E gap. E chi plus E gap is the energy difference between the vacuum level and the semiconductor valence band edge. Subtract the metal work function, you get the Schottky barrier height. And in the Richardson-Dashman constant, same expression holds for the Richardson-Dashman constant, except you need to replace the electron effective mass with the hole effective mass, because now it is the holes which are the majority charge carriers which participate in the current formation. So we are done with the metal semiconductor contacts. Thank you all very much for your kind attention. Goodbye.